Welcome to our chapter, Dispatchable Solar Power Technologies. In this video we define the term dispatchable power. We give an overview of dispatchable solar power technologies. We show their different resources of solar radiation. And finally we provide characteristics of each dispatchable solar power technology and its components. Our definition of dispatchable power is based on three components: stability, availability, and reserve. Stability means to provide energy according to demand. This is especially important to supplement fluctuating renewable energies and cover the remaining demand adjustable and flexible. Availability means to provide power at the instant of time when it is needed. Due to a 24/7 demand of electricity, dispatchable power must be available at any time. The term reserve focuses on the ability to provide capacity and energy securely. This means having enough backup capacity as well as short to long-term stored energy. Our definition of dispatchable power is therefore summarized in one sentence: flexible supply according to demand at any time with firm capacity and firm energy.
Dispatchable solar power technologies can have various components and combination possibilities. This is especially important providing flexible supply according to demand at any time with firm capacity and firm energy. To collect the sunlight, different types of solar collectors can be used. We distinguish between collectors which concentrate the sunlight via mirrors, called concentrating solar power, and modules with photovoltaic cells. Concentrating solar power collectors focus on spots or pipes which contain a heat transfer medium. This heat can be stored short-term in storages or converted via steam turbines and generators into electricity and subsequently transmitted to centers of demand. As backup options, steam turbines can be co-fired with waste or biomass to provide firm capacity. Photovoltaic cells generate electricity directly inside the module. The challenge consists in storing the electricity and providing enough capacity at night. The concept of dispatchable solar power using only photovoltaics is still in a lower technology readiness level at the time of publishing this video and therefore only shown conceptually. A solution of storing electricity provided by photovoltaics could be using high-temperature heat pumps. This could allow subsequently the same thermal process as previous mentioned with concentrating solar power. Beside the conversion process from thermal to electrical energy, it is also possible to convert thermal or electrical energy into chemical energy such as synthetic fuels. This process could have a use case for energy sectors which can't be accessed easily with electricity. This affects shipping, aviation sector, and mobile construction industry. Fuels can be then transported, for example, via pipelines to centers of demand. However, the conversion into chemical stored energy has a physical disadvantage due to a low efficiency factor. Providing 1 kilowatt-hour of chemical energy for fuel production needs around 2 times more energy than providing 1 kilowatt-hour electrical energy. This results in the construction of around twice the amount of power plants. In the following we focus therefore only on the provision of electrical energy for the electrical supply system. However, using the advantages of each technological component in a specific mix can lead to synergies and therefore to a win-win situation benefiting from the versatility of a technology combination with different use cases. Collectors for concentrating solar power use the so-called direct normal irradiation. This irradiation incident orthogonal on the solar collector, which requires tracking the position of the sun. Modules with photovoltaic cells can use the global horizontal irradiation, which consists of diffuse irradiation and direct horizontal irradiation. A tracking of the sun's position is therefore not obligatory for photovoltaic modules. The resources direct normal irradiation for concentrating solar power and global horizontal irradiation for photovoltaics lead to different technological yields. We show the yield as a function of the collector power output availability. The presented plot is a so-called isopleth diagram which shows in our example the collector yield in North Africa hourly of each day for 1 year. In North Africa the yield of solar irradiation is almost constant during the year due to proximity to the equator. The presented plot also shows the nearly continuous day and night cycle over the year, which enables a short-term storage use case providing energy day and night almost constant during the year. The yield of the concentrating solar power collector has a high availability during noon and summer months. However, this high availability is not perfectly continuous and rather scattered. This is the case due to clouding and absence of direct normal irradiation. The yield of the photovoltaic module has also a high availability during noon and a smoother trend due to almost constant available global horizontal irradiation. However, the intensity of the availability is not that high compared to the concentrating solar power collector, resulting in a lower efficiency factor of the photovoltaic module.
The solar tower technology is a point-focusing concentrating solar power technology and consists of so-called heliostats tracking the position of the sun and focus the sunlight to a receiver on the top of the solar tower. In the solar tower, a heat transfer medium, often molten salt, is heated up to 1000 degrees Celsius and transported to a thermal storage or converted via a steam turbine and a generator into electricity. In our example, we show the Ivampa solar towers with a gross capacity of 392 MW built in California, USA in the year 2014. The parabolic trough technology is a line-focusing concentrating solar power technology and consists of reflectors in parabolic shape which focus the sunlight on a receiver in tubular construction. In the receiver, a heat transfer medium is heated up to around 400 degrees Celsius and transported to a thermal storage or converted via a steam turbine and a generator into electricity. In our example, we show the Andasol parabolic trough system with a gross capacity of 150 MW built in Andalusia, Spain in the year 2009. The linear Fresnel technology is a line-focusing concentrating solar power technology and consists of reflectors built in strip shape which focus the sunlight on a receiver in tubular construction. In the receiver, a heat transfer medium is heated up to around 400 degrees Celsius and transported to a thermal storage or converted via a steam turbine and a generator into electricity. In our example, we show the Durser linear Fresnel facility with a gross capacity of 125 MW built in Rajasthan, India in the year 2014. Due to remaining space underneath the reflectors, agricultural utilities could be a synergetic combination which could allow growing food and using fresh water from mirror maintenance.
Photovoltaic cells generate electricity directly inside the module. As previously mentioned, it is the challenge in storing the electricity and providing enough capacity at night. The major drawback for a large-scale electricity battery storage today is the limited capacity, high investment cost and environmental impacts. To store electrical energy, a conversion of electricity into heat could be a solution using short-term heat storages. Hereby, a high-temperature heat pump is necessary. The heat temperature should be in the range of 300 degrees Celsius to enable a steam turbine process and the operation of an electrical generator. One major challenge is still to find a suitable heat transfer medium for a high-temperature heat pump. Thus, photovoltaic, at the time of publishing this video, is only a conceptual possibility of a dispatchable solar power technology.
In this video, we define that dispatchable power is flexible supply according to demand at any time with firm capacity and firm energy. In our example, the yield of solar irradiation in North Africa is almost constant during the year due to proximity to the equator. This results in a nearly continuous day and night cycle over the year, which enables a short-term storage use case providing energy day and night almost constant during the year. Dispatchable solar power could therefore be a major supplemental component for the energy system, providing flexible supply according to demand at any time with firm capacity and firm energy. Regions which do not have this renewable resource may only need to create suitable frame conditions and overcome the distance via transmission infrastructure and trust in cooperation. An old African wisdom says, "If you look in the direction of the sun, you leave the shadow behind." Feel free to follow and contact us via social media or email.